Good day. So, today's topic is IP multicasting. Till now, we have seen, there are three modes of operation. One is unicast, that means when one sender is sending to one receiver. One is broadcast, that means one sender sending to all the receivers, that means all the nodes in the network, and multicasting, that when you want to send it to just a group of hosts, not all the hosts. So, that is the topic today, IP multicasting. Now, so as I said that multicast communications refers to one to many or many to many communications. For example, over here this is unicast, when the source is one, destination is one. Broadcast, when source is one and destination is all, and multicast, destination are a few. Okay. So, IP multicasting refers to the implementation of multicast communication in the internet. Individual hosts are configured as members of different multicast groups. Multicasting is not connection oriented. So, an IP multicast group is identified by a class D address. So, these are the general parameters. One thing is that of course, one particular user may be a member of different multicast groups, but anyway for one particular multicast groups there will be a few members in the network and it has to reach those and not others. And the other thing to understand is that multicasting is not connection oriented, that means all the packets are sent. That means it is packet by packet. It is not that from the source multiple channels are a priori set up or anything like that. And this they are identified by a class D address, which is for multicast. So, for the class D address is seen in this fashion, that the beginning 4 bits are 1110. So, the initial value is 224 point something, and these 28 bits. There are I mean something about these 28 bits, I will come to these later on, but this is how you can by looking at an address you can see that this is a multicast address. There are many applications, for example, news, sports, stock, weather updates. Now, let us take any example, let us say some stock update. Okay. Now, stock updates, not everybody would be interested in stock updates, only some groups of people would be interested in stock updates. Then again it may be such that one group of stocks is of interest to one group of people, another group of stock to another group of people. So, these would be different multicast groups, and the news feed should reach these people. Then multicasting may be applied in distance learning when some learning material is distributed to distant learners and just a specific group of learners. Configuration, routing updates, service location. So, these may be the multicast may be applied here. Point cast type push applications. Push means when the actual source of information it finally it on its own sends it to a group of people. Okay. For example, you for example, say the stock quotes, that may be pushed. Teleconferencing, audio, video shared, whiteboard, text editor, etc. That is an interesting and important application of multicasting. That means you may like to have a video conferencing amongst a group of people. All right. So, this video stream should reach, the same video stream should reach all these group of people. Distributed interactive gaming or simulations. So, some people are in a distributed fashion, they are participating in some game. Email distribution lists, content distribution, software distribution, web cache updates, database replication. So, you see multicasting has very large number of applications, but of course, the trouble is multicasting is a little complex. I mean the technology is not so simple, and the fact is there are most of the routers which are on operation today, they are not configured for multicasting in a proper manner, because it takes a toll on the router's capabilities. So, we will come to see what multicast routing is all about. Now, there are three essential components of IP multicast service: IP multicast addressing, how you address, IP group management, and multicast routing. If you look at this diagram, suppose, so you have, let us say, these three routers here and three networks connected to the three routers respectively. Now, this router, suppose I take any of these routers and that is connected to its own group of machines, and this machine, these machines, some of these machines would be the members of a multicast group. And of course, new machines can come in and or new machines can actually decide to join the multicast group, and the old some of the old group members, they may choose to leave a particular multicast group. So, there is a group membership protocol which goes on between the router and the different machines connected to the network. Then amongst the routers there is a question of multicast routing. This internet management group management protocol, that IGMP, that runs between host and their immediately neighboring multicast routers, and within the routers we have the multicast routing protocol running. So, this is another picture showing the same thing. So, this is the service model. Suppose these are the hosts and a host to router protocol, which is known as the internet group management protocol or IGMP, and then there are amongst the routers there is this multicast routing protocol, and there are various types of multicast routing protocols. We will just discuss a few. Now, IP multicasting only supports UDP as higher layer, there is no multicast TCP. Okay, UDP, as you know, is a connectionless datagram oriented protocol, and TCP is connection oriented. Since IP multicasting is essentially connectionless, so that is why it chooses UDP as the transport layer protocol. So, if you look at the details of the this part of the protocol stack here, we have the network interface and the IP and IP multicast layer. So, the IP and the IP multicast layer, so the IP part of this network layer, that takes part in the normal routing protocol, whereas IP multicast part, that takes care of the multicasting routing protocol. And then above this, in the TCP IP stack, we have the TCP protocol and the UDP protocol. So, for TCP we know that we use stream sockets, whereas for UDP we use datagram sockets as well as multicast sockets. So, multicast sockets also use UDP. So, this is the socket layer. Above this we have the user layer. So, that is the application layer, which uses these multicast sockets and uses UDP to go through IP to send multicast messages, which are routed by the multicast supporting router. So, this works as follows: multicast groups are identified by IP addresses in the range 224.0.0.0 to 239.255.255.255. These are the class D addresses. Every host, or more precisely the every network interface card, can join or leave a multicast group dynamically. There is, at present, the way it is done, there is no access control. So, if there is a multicast group which requires access control, then this has to be implemented in the application layer, but this cannot be I mean as the protocol stands today, this has not been included. One of the reasons is that IP multicasting in actual practice constitute a very small amount of traffic compared to its potential true multicasting. We will see what I mean by true multicasting and sort of simulated multicasting later on, but true multicasting, actual true multicasting traffic is really small compared to its potential, mainly because most of the routers, let us say, they may not support it, or they are not, more precisely, they are not configured to support multicasting because of the costs involved. So, since there is no access control, every IP datagram sent to a multicast group is transmitted to all members of the group. There is no security, no floor control. And moreover, since it uses UDP, IP multicast service is essentially unreliable. Talking more about the I mean a little more detail about the multicast addresses, the range of addresses between 224.0.0.0 and 224.0.0.255, that means the last byte for the first range inclusive, is reserved for the use of routing protocols and other low level topology discovery or maintenance protocols. So, we will see some of this, and multicast router should not forward any multicast datagram with destination address in this range. So, they are reserved addresses, other addresses can be distributed to different multicast groups. For example, special reserved class C, some examples, say 224.0.0.1, this really means all systems on this subnet. 224.0.0.2, all routers on this subnet. 224.0.1.1 is for NTP, that is the network time protocol, which is used for synchronizing machines. 224.0.0.9 is for RIP2, a routing protocol. So, these are some special addresses, and there are others. Now, there is a question of multicast address translation. You remember that what happens in the case of unicast, that from the address, from the IP address, we usually in the local network for transmitting packets in the local network, we need to go down to the data link layer and need to find out the hardware address. Let us say if we are using Ethernet, then we need to find out the Ethernet or MAC address, and then data is actually sent as a frame, Ethernet frame. Okay, so the Ethernet address is put over there. Now, that is the case when we are handling unicast. Now, what happens in multicast? The point is for this particular IP address is actually representing a particular multicast group, and there will be a number of machines in that group. So, but how do you handle it in the Ethernet level? Well, in Ethernet MAC addresses, a multicast address is identified by setting the lowest bit of the most left byte. That means this byte. Suppose so 1, 2, 3, 4, 5, 6. You remember that a Ethernet address is 6 byte long. Now, of the first byte, most significant byte if you want, if you like, and the last bit of that is set to 1 in Ethernet MAC addresses to indicate that this is a multicast address. Unfortunately, not all Ethernet cards can filter multicast addresses in hardware. So, if it cannot be done in hardware, then filtering is to be done in software by the device driver. So, you accept the packet and then do the filtering, that if it is multicast and if you are a member of the group, then accept it. And this is how the mapping is done. So, suppose this 1.1.1110, the first 4 bits of the most significant. So, this is suppose a class D address, and we are looking at the first byte of that address, and the first 4 bits 1110 identifies that this is a class D address. Okay. Then this bit is actually ignored, and then we have a 23-bit address. This 23-bit address comes straight to the Ethernet address. So, these 7 bits, these 8 bits and these 8 bits, they are mapped straight to the last 3 bytes of the Ethernet address. For the first 3 bytes of the Ethernet address, we have a 1 here showing that this is a multicast. Actually, the Ethernet address with 01005E in the first 3 bytes are reserved for IP multicast. So, 0100 and this is 1011 is 5, 101 is 5, 5E, 1110 is E. So, 01005E, this is first 3 bytes, this is reserved for multicast, and this part comes straight away. Now, let us move on to IGMP, which is the Internet Group Management Protocol. So, this is a very simple protocol for the support of IP multicast. IGMP is defined in RFC 1112, and IGMP operates on a physical network, that is a single Ethernet segment. So, if you remember the previous diagram that we had shown, that one particular router connected to one, let us say, Ethernet segment. So, IGMP is between this router and the hosts which are there. Okay. So, IGMP is used by multicast router to keep track of the membership. Now, who all amongst these are members, who has ceased to be a member, who is the new person who wants to join as a member. So, this is the this has to be kept track by the local multicasting router. So, that is what IGMP supports. So, it supports joining a multicast group, query membership, and send membership reports. So, the query membership, so the multicasting router will send queries from time to time, and the host will respond or not respond depending on whether or not they are members of the group. So, we have this multicasting router over here and one single Ethernet segment, a number of machines connected there. So, IGMP query comes from this multicasting router, and IGMP report goes to the router from the hosts. So, there may be a IGMP general query, that IGMP group address is set to be is equal to 0. That means, this query is for all the hosts, for all the groups, and destination IP address is this broadcast in this subnet. You remember this 224.0.0.1 is broadcast in this subnet, and source IP address is the router's IP address. Or there may be group specific query, in which case the IGMP group address is the group address, destination IP address is again the group address, because now I want to give this query only to the members of one particular group. Source address is the IP is router's IP address, and these individual hosts send the report. So, IGMP membership report. So, IGMP group address is the group address, destination IP address is once again the group address, and source IP address is equal to host IP address. And there are various I mean in the IGMP message format there is a version which is type maybe 1 or 2, version is usually 1, and then the 16-bit checksum and 32-bit group address. Type is a 1 is a query sent by multicast router, and 2 is a response sent by a host. Group address is a class D IP address. On query it is 0, on response it is the group's address being reported. And a host sends an IGMP report when it joins a multicast group. Note, multiple processors on a host can join. A report is sent only for the first process, which means that when a host wants to join one particular multicast group, then it sends an IGMP report to the router that okay, I want to join. Now, when on the other side, when a particular host wants to leave a group, I do not want this multicast traffic any longer. So, when I want to leave that group, I do not do anything at all. Okay. Only thing is that when when the next query comes for this particular group of which I was an erstwhile member, I will not respond. Okay. So, this absence of response, so which means that there is some kind of aging in the group membership list that the router would maintain. So, no report is sent when a process leaves a group. A multicast router regularly multicasts an IGMP query to all the hosts. Group address is set to 0. A host responds to an IGMP query with an IGMP report. If somebody fails to respond, then it is taken as that he has left the group. So, what does the IGMP host response reports look like? Host sends a report when it joins a group, does not report when it leaves the group as I mentioned, but does not respond to the next query. So, this is IGMP report, time to leave is 1, IGMP group address is group address, destination is group address, and source IP address is host IP address. And query, for query, group address for general query, group address is 0, destination IP address is naturally based broadcast, and source is the router's IP address. So, router sends query at regular intervals to see if anyone still belongs to any groups. Query is sent out each interface, and host responds by sending one response for each group to which it belongs. So, IGMP messages are only 8 bytes long. So, you have Ethernet header, IP header, and the IGMP message, which is version type, and some part is unused, and the checksum and some 32-bit class D address. Suppose you have a network with multiple multicast routers, that means the same network, but it has got multiple multicast routers. So, only one router responds to IGMP queries. So, this is the querier. So, router with the smallest IP address becomes the querier on a network. One router forwards multicast packet to the network. So, that he is the forwarder. So, what I was saying is that if there are multiple multicasting routers, if a network happens to be so constituted that there are 2 routers connected to it and both of them support multicasting, in that case only one router will actually do the querying. So, out of these 2 routers, whichever has the smaller IP address, that is the one which will do the querying. Now, we come to the topic of multicast routing. So, what is special in multicast routing? Let us see this diagram. So, suppose there is no support for multicast at the network layer, which is the case in many practical situations. So, even then, so what you could do is that you could sort of simulate multicasting sort of by doing repeated unicast. So, your original source has a list of all the members, that means list of all the members meaning their IP addresses, so he sends the message to all of them one by one, one after the other. So, this is just a stream of or successive unicast which is done. So, this is as if a multicast. Obviously, you are sending more packet totally, more packets are packet into hops. If you just take some measure like that, of course, you are doing much more work than what is strictly necessary, but this is all you can do. This has of course has an advantage that the source can closely control that who would be a member of the group and who would not be a member of the group. He can you can impose some kind of access control by having a access list. Now, if there is support for multicasting, then what would happen is that the source would send only, let us say there is one packet is being sent to all the 3 members of the group, say this is the source. So, source will send only one packet to the next router. This router is going to duplicate the packet, one on this link, the other on this link. This packet is ultimately destined for this host, whereas this packet again gets multiplied, and now this packet goes to this host and this packet goes to this host. So, the number of packets travelling down is minimized a lot compared to final number of packets of course is the number of users, but if you just consider that how much each packet travel, that means if you take the number of packets into hop count, that kind of an weighted measure, then this would be much lower overhead in some sense, that means for packets travelling. So, it is much lower overhead on the links, but maybe more overhead on the routers. Now, this requires, if you have to have this multicasting capability for the routers, you have to this requires specifically 2 things. One is packet forwarding can send multiple copies of the same packet. For example, consider this router. This router only one, it is receiving only one packet, but it has in its list that there are two sort of users for which the packet is supposed to go through this router. So, it has to duplicate the packet, one for this link and the other for this link. So, it forwards the packet multiple copies of the packet. This capability has to be there in the router, that is the first thing. And secondly, multicast routing algorithm which builds a spanning tree dynamically. That means that who gives you this tree, that is a, I mean, how do you form this tree? This looks somewhat similar to forming a routing tree for unicast cases, but there is some differences. So, this tree has to be built up dynamically and in a distributed fashion by the routers. So, for that they have to run some multicasting protocol, IP multicasting protocol between themselves. So, that is what we mean when we say that the routers are supporting multicast. So, the main goal of the multicast routing protocol is to build a spanning tree between all members of a multicast group. So, these are the members of the multicast group, we have to somehow get this tree. So, this can be looked upon as a graph theoretic problem. I am afraid that this is not very visible. Let me anyway, so whatever tree, whatever graph you have to embed a tree such that all multicast group members are connected by the tree. So, suppose these are the different members of the multicast groups, these are the 3 members of the multicast group in the previous graph. So, I want to form a tree like this. One solution is to have a shortest path tree or source based tree, that is, a build a tree that minimizes the path cost from the source to each receiver. So, this is a this is the so called source based tree. So, you can form this. So, this is one kind of solution. So, this is called a source based tree. This is a good tree if there is a single sender. So, sometimes a multicast group is such that there is a single sender. For example, take the previous example we were talking about. Say we have the say from a central news service or some kind of financial advisory service, it has some members. So, these are the members of his multicast group, and some stock quotes he is going to the. So, this particular group maybe is interested in the quotation of a particular group of stocks. So, for this particular group of stocks, this company would collect all the information and the stock value etc., in a regular fashion and keep on pushing to this multicast to these members of this group. Now, this is multicasting, of course, where there is a single sender, and in such cases making a source based tree makes quite a lot of sense. But of course, if there are multiple senders, you need one tree per sender. Now, that becomes really difficult. When the number of members in the group, that means it is a more democratic kind of group where the group members are interacting. Any of them maybe can send a message to all the other members of the group. Now, this becomes quite difficult. That means you have to have a tree for each sender. Having this single sender, this of course is easy to compute. Of course, we for this multicasting protocol, multicasting router, we will always assume that the unicasting routing, whatever is happening through RIP or OSPF or whatever that unicast routing, that is already there. This multicast is sitting as an additional service by the router, which essentially means that the unicast routing table is available for building up your source based tree. So, this is so in such a case this is easy to compute. Tree is built from receiver to the sender. This is called reverse shortest path or reverse path forwarding, RPF. So, what is RPF? We will see, that we will see when we come to the details of this protocol. A second solution to the same problem is that if you remember the other graph, this graph looks different because this is a graph where it minimizes the total cost of the edges. If you do not know who your sender is going to be, that means if any member of the group can be a sender, then of course it makes sense to make the tree in such a manner, assuming that I mean, suppose if you assume that all of them send packets equally frequently, in that case having a tree with the minimum total cost of edges, that would be the optimal solution. So, this is a second kind of solution. This is called I mean something, and this is of course very difficult to compute. This is called something close to this people try to compute, and that is called a core based tree. So, it is a good solution if there are multiple senders. So, instead of keeping one tree, one source based tree for each potential source, so we keep one core based tree, but very expensive to compute, not practical for more than 30 nodes for a very good solution. It selects one router as core, also called the rendezvous point, and all receivers build the shortest path to the core using the once again the reverse shortest path or reverse path forwarding. But who would be the core or the rendezvous point, depending on that, I mean how good your core based tree is depending on how you choose the core. If the core is, if you have chosen the core towards the center of the potential graph, then that is good. Now, let us see the details of reverse path forwarding. RPF, this is the way to build the tree. RPF builds a shortest path tree in a distributed fashion by taking advantage of unicast routing table. The main idea is the following: given the address of the root of the tree, you know the source, actually this tree is being formed by from the sources. So, from the sources they are all trying to reach the from the destination. From this destination, each of the destination, that means each of these potential recipients, they are trying to reach up to the source, and for that they use the unicast routing table which is already there on the router. So, given the address of the root of the tree, a router selects as its upstream neighbor in the tree the router which is the next top neighbor for forwarding unicast packets to the root. So, basically what you do is, since you are trying to minimize the for each of the potential recipient, you are trying to minimize the path cost from this recipient to the one single source. Right now, for the source based tree we have one single source. So, naturally whatever you do for unicasting for while sending a message from this node to that node, that is what you try to follow. What the routers have to do is that on the way, suppose there are two different routes, potential routes from two different recipients go through the same router, then from this point onwards it is expected, since this router to the final destination, which is actually the source of multicast communication, there is only one path. So, the tree would be automatically formed. So, that is the basic idea of reverse path forwarding. So, how can this be used to build a tree? RPF forwarding, forward a packet only if it is received from an RPF neighbor, and set up multicast routing table in accordance from receiver to sender along the reverse shortest path tree. So, it is simple as that. Say this is an example. Suppose H1 is the source, H1 is the source, and RPF neighboring neighbor of R3. This is R3. So, this is R4, R1, R4, R5. Now, from these, when they try to reach say H1, they go from 2 R3 to R2 to some this thing path to H1. So, this is the RPF neighbor of R2 is the RPF neighbor of R3. So, so the destination is H1 and the next hop is R2. This is the unicast routing table. So, you know that this is the RPF, R3 knows that R2 is the RPF neighbor of itself. So, that is how. So, routing table entries for source based trees and core based trees are different. For source based tree it is a source group or SG entry. For core based tree naturally anybody can be communicating. So, it is star comma G entry. So, so the source IP address, multicast group, which multicast group, incoming interface, that is RPF interface, and outgoing interface list. So, these are the L2, L3 etc. So, this is a list, and finally, when a packet arrives the router has to forward one copy of the packet along each of these links, outgoing links, which eventually reach some members of this particular multicast group. So, for building a source based tree in a network like this, so set routing tables according to RPF forwarding and then use flood and prune. So, we will discuss this. Set routing tables according to RPF as we have already discussed, and then do flood and pruning. What is flood? Forward packets that arrive on RPF interface on all non-RPF interfaces. Receiver drops packets not received on RPF interfaces. Okay. That means first thing is that it as I mentioned that these routers require the capability of forwarding multiple copies of the same packet. So, if a packet has come from from its RPF neighbor, which means that for this particular RPF neighbor is of course with respect to a particular group. Now, so if a packet has come from that RPF neighbor bearing this address, so which means that it is actually coming from the source. So, now it has to be forwarded to each of the outgoing interfaces which are each of the outgoing interfaces. Of course, there is a non-RPF, that means when I say RPF interface, it means that the RPF neighbor, that means it is coming from the sources side to all others which lead to different members of this multicast group. Now, what happens if you happen to get a packet from a link for this particular group who is not your RPF member? First of all, how did it happen? Of course, it can happen because you must remember that we are doing this in a distributed and dynamic system. So, things can come up and go down, so that way a packet can come in, but obviously this is not meant for I mean so far as this particular router is concerned, if a packet comes from a non-RPF link for this group, then this is not coming from the source. So, that packet is dropped, and actually there is something else it does, that is pruning. So, what is pruning? Pruning is send a prune message when a packet is received on a non-RPF interface. This is one case when you prune, or when there are no group members in its local network and no connection to other routers. Suppose it so happens that this particular router, you remember that this router is also connected to its local network, and with the host in the local network it is running IGMP, always finding out that who are the members of the group, etc., etc. It could happen that this local member has retired. Okay, he no longer wants to be in the group, that means he is no longer sending your IGMP reports. So, he has nobody to send it to, nor is he connected to any router, that means nor is he a part of a link from a distant source to a distant destination. Okay. So, nor is he a transit link like that. So, it is not connected. In that case also maybe so that this his local contributor member of the group has retired, this of course may not be known to others. So, they may still he may still get a packet, but then what he will do is that he will send a prune message, that means do not send this send me any more packets any longer. So, he will send a prune message along that route, because from that from that neighboring router has sent in a packet, he has nobody to distribute it to. So, not and nor is he a transit router. So, naturally he drops this packet because he has no use for this packet, and along this link whoever had sent him that packet, to him he sends a prune message, that means do not send me any further packets because I have nothing to do with this group anymore. So, that is one case. Or has received a prune message on all non-RPF interfaces, that means all the non-RPF interfaces he was member earlier, just like as the group member may have retired, similarly he may have been a router on a transit router on a link from some source to some destination, distant source to distant destination, he may be a intermediate router on the way. But then he has got a prune message on all its non-RPF interfaces, that means he was a member of a transit link earlier, but now he is no longer a member. So, once again he will, whoever had sent him a packet, he will send a prune message to him that prune this link as well. So, this is I am no longer interested. Okay. Now, prune message temporarily disables a routing table entry. Effect removes a link from the multicast tree. No multicast messages are sent on a pruned link. So, prune message is sent in response to a multicast packet, a multicast packet which has come and which satisfies any of these conditions. Once again, that it has is received on a non-RPF interface, or when there are no group members in its local network and no connection to other routers, or it has received a prune message on all non-RPF interfaces. So, in such cases the prune message is sent. So, the prune message has the effect of temporarily disabling a routing table entry. The question is, why temporary? Well, why the routing table is only temporarily disabled? Well, what happens is that you may have a receiver who may again like to join. So, one needs to reactivate a pruned routing table entry in that case. So, what happened is that this group member, maybe he had gone away somewhere and now he has come back and he wants to be a member of the group once again. So, he gets a report, IGMP report, saying that okay, I am a member of this group. Now, he knows that who knows the source, this multicasting router. So, what he will do is that he will try to reactivate this link, and then the rest of it will work. So, this is called grafting. Sending a graft message disables prune and reactivates the routing table entry. So, this pruning and grafting, these are complementary to each other. You prune to disable and you graft to enable you again. The next, this thing is the core based tree. You remember that this was a source based tree when you have one source and many receivers. Now, you have many to many kind of situation. So, that was one to many kind of communication, not one to all, not broadcast, one to many, but now we have a many to many communication. That means, there are many members of the group who might like to communicate with other members of that group. So, in this case we would like to have a what is known as a core based tree. So, one router is the core and receiver sends a join message to RPF neighbor with respect to core. Now, every receiver actually wants to join to the core. So, join message creates a star G routing table entry and source sends data to the core. Core forwards data according to the routing table entry. Now, since there is no source, or that anybody could be a source, so we put a star in place of S. So, all the links which get for a particular router, all the links which get messages like this. So, they may, I mean, a message may come in through any such link, and it has to be forwarded to all the other links. Okay. Now, we just mention about multicast routing protocol, which is actually implemented in most of the routers and many of the level 3 switches also. This is called DVMRP. So, you find them actually, but unfortunately I have seen it very rarely being used, but this is there in most of the routers of today as well as many of the layer 3 switches. DVMRP is there. So, this is a distance vector multicast routing protocol. Okay. So, this is the first multicast routing protocol, and it implements flood and prune. So, and there is another this thing, just as RIP gives you the distance vector vector routing. If you remember, the distance vector routing is the distributed Bellman-Ford algorithm, which is implemented by RIP, and the centralized Dijkstra's algorithm, the link state algorithm, is implemented in the routing protocol called OSPF, Open Shortest Path Fast. If you remember, recall our discussion about routing protocols, and this OSPF is the currently most acceptable routing protocol. And there is a multicasting version of OSPF also, which is known as MOSPF, Multicast Open Shortest Path First. So, multicast extension to OSPF, each router calculates a shortest path tree based on link state database. This is not very widely used, and there is a PIM SM, so there is a sparse, and there is a PIM DM also, which builds core based trees. So, they are there, but they are not very widely used. So, we will not discuss this. Now, in distance vector multicast routing, DVMRP consists of two major components: a conventional distance vector routing protocol like RIP, and a protocol for determining how to forward multicast packets based on the unicast routing table, that is that flood and prune part. So, DVMRP distance vector multicast routing, these routers say that they forward a packet if the packet arrives from the link used to reach the source packet. And that means you remember that actually we are doing, this is the reversed path forwarding part. That means if from this router I want to reach the source, if I want to reach the source, then I have to go to that is the next hop I am taking. So, that is my RPF neighbor. So, if the packet arrives from this link, from my RPF neighbor link, arrived from the link used to reach the source of the packet. So, this is the RPF check, and packet forwarded only to the child links, not to the not in the direction from which it came, but to other child links, if provided the downstream links have not sent a prune message. But DVMRP has limitations like distance vector protocols affected by count to infinity and transient looping. You remember that count to infinity problem, that some link has failed, but nobody could understand whether nobody could make out that the link has actually failed. So, it was going round and round. So, that is that count to infinity, and they all keep on counting the potential distance to that, and it counts to infinity. That is a count to infinity problem. Since we are using the same distance vector routing, so that is there. Transient looping, that means sometimes a loop may form, a routing loop, that means and the packet goes round and round, that is also there. And multicast trees are more vulnerable than unicast for these problems. Okay. So, why we are not going into the details of this. this shares the scaling limitations of RIP. So, new scaling limitations are, and this scaling limitation essentially comes from what I have written at the last, that no hierarchy. This is a flat routing domain. You remember, in order to I mean one of the advantages of OSPF over RIP was that that when the routing problem became very big, because as network grew bigger and bigger, so there was a in OSPF we build it up into a we break up the network into a hierarchy. There are these autonomous regions or autonomous domains, and then further down you can be broken up. So, there is broken into hierarchy, so that the routing problem remains simpler, so that you can scale to bigger and bigger network. Since DVMRP is based on RIP or essentially on the ideas of RIP, so that is not that is again a problem in DVMRP also. That is the problem, you cannot scale, and then you have some further problems because of multicasting. So, you may have SG state in routers even in pruned parts. Then broadcast and prune has an initial broadcast. Okay. When I say flood and prune, so actually you are flooding the network. So, there is some kind of broadcast going on, and this broadcast, if the network size is small, this broadcast may be acceptable, but when the network grows bigger and bigger, broadcast becomes unacceptable. So, that is again another problem in scaling, and this is limited to few senders, many small groups also undesired. So, since this essentially forms a source based tree, so you can have only just a few of them, just a few senders. Many small groups are also undesired. If you have a large number of groups, once again you have the same problem of maintaining so many trees, alright. So, that also becomes a limitation for scaling. Okay, and now we just talk about one effort to sort of implement multicasting. So, because as I told you that most of the routers they are not configured to use the multicast in every manner. So, but then still some people want to use multicasting. So, what they did was they built up this multicast backbone MBone, which is essentially an overlay network of IP multicast capable routers using DVMRP. So, it uses DVMRP and it is an overlay network of IP multicast capable routers. What does that mean? That means that some of the routers in the network in some places they are multicast capable, and what happens is that they are going to support multicasting in its own locality. That means, it will support multicasting amongst the network to which they are directly connected, that is one thing. And then these routers are going to run a multicasting protocol between themselves, but then in between there are a whole lot of other routers, in between there is a cloud of routers, let us say, which are not supporting multicasting. So, what it will do is that it will tunnel through this cloud to the next multicast supporting router. So, this is the picture of the MBone. So, we have say R is the host or the router, and this R they are the, and this H. So, these are the MBone router. So, these are the MBone routers, they support. So, this part of the MBone is shown in light blue, that means this part is shown in light blue. So, there the multicasting is directly supported, whereas when they try to communicate to another multicast supporting node over a cloud which do not support multicasting, they tunnel through it. So, that is the idea. Okay. So, MBone tunnel is a method of sending multicast packets to multicast ignorant routers. IP multicast packet is encapsulated in a unicast packet. So, this is an IP in IP addressed to the far end of the tunnel. So, if you look at it, you have the IP header destination is unicast, then you have another IP header destination equal, that is the multicast, and then the transport header. So, what happens is that the intervening routers who are not multicast enabled, they are going to see this destination, and this destination would be then actually the next multicast router. So, they are going to, and this part will be the payload. So, the network nodes would not look into this. When it reaches the next multicast supporting router, he will not only look at the, I mean he will of course get this and then discard this, then look at this multicasting header. So, this is the IP and IP encapsulation and tunneling. So, tunnels act like virtual point to point link. Intermediate routers see only router header, that means that the unicast routing header. Tunnel endpoints recognize IP in IP, protocol type equal to 4, and decapsulates the datagram for processing. Each end of the tunnel is manually configured with unicast address of the other end. So, this is what you have to do. So, this was done to implement multicasting in an environment and try it out. But as I said that if there are many, there are problems about the one which is actually implemented in most of the routers, namely DVMRP, that does not scale well, and naturally if there are many groups, and in today's world when everybody is sort of networked and people have all their special interests, etc. So, it is quite conceivable that the number of groups will explode if people could really do multicasting in a very easy fashion, and that is very difficult for routers to handle. So, that is why most of them do not use it at the moment, but potentially this is a very useful kind of technology. Thank you.
Good day. So, today we will talk about some protocols which are useful for controlling the network and sort of making machines connected to the network. Specifically under the broad class, we will talk about DHCP and ICMP. So, there are some protocols associated with this, so we will talk about those. So, DHCP is dynamic host configuration protocol. Okay. So, it is about configuring a host, configuring a machine, configuring maybe a PC or some computer which is connected to the network. Its chief utility, I mean, well, there are other utilities of DHCP, we will come to that later, but then its chief motivation came from dynamic assignment of IP addresses. Now, dynamic assignment of IP addresses is desirable for several reasons.